Rita. Good
Good
afternoon,
afternoon.
everybody.
Thank you.
Yeah. My name is Maruf Adewole. I'm a medical physicist at Marcel's Cancer Center. Apart from that, I'm equally a doctoral student at the University of Lagos. My research work centers around the application of artificial intelligence in radiotherapy, and the situation demands radiology in some instances. So today I'll be giving a talk, more like a conversation on artificial intelligence and medicine. And I equally want to appreciate everybody who has been part of this program since Monday. The commitment you've demonstrated shows that you are going to be a medical physicist. It's one of our core values to make sure that when we put commitment to something, we see it too. So without much ado, let's get started. Artificial intelligence, from those of us who grew up watching movies like Transformer, movies like Terminator, this is what comes to mind. A particular robotic element who has all the powers beyond human comprehension. But by and large, in not too long distance to come, we'll be having artificial intelligence in this kind of form. But it is equally with us right now and then in the form of gadgets, our mobile phones and our laptops. But before we proceed, I would like us to quickly do an exercise right now. If you have access to a browser, just flip it open. Go to google.com and type physics, open another browser, type medical physics. And the first options that you are going to get without clicking enter, just press spacebar, is going to give you some options. I want you to take the first option it gives you when you type physics and when you type medical physics and put it in the chat box. For this presentation, we are still going to talk about this and not to as the presentation proceeds. Okay, so moving ahead, apart from that, we equally have application of AI to things around us. We have the feature components of it analysis, those that help us to do sentiment analysis, functional AI, robotics, chatbots, text-to-speech recognition. These are part of the things that augmented reality and so on. These are part of the things that we've already been using. Moving ahead to the subject of discussion for today itself, this is my outline, introduction to AI, general application, the pros, the models, machine learning, and so on and so forth. So by and large, moving to the definition itself, what is artificial intelligence? It's a branch of computer science devoted to creating systems to mimic human intelligence. It can also be defined as the creation of intelligent machines that work and react like humans. Another definition is also building a machine that can reason, plan, learn the same way that humans can also do. And it is getting increasingly sophisticated due to the fact that we are having increase in computational power. A lot of people are getting involved into it. We have new algorithms, the data sets are expanding, and we are just the things we can do with AI are becoming more and more diverse, and we can only be limited due to how much we can imagine in this particular field. Moving ahead, for people among us who use iOS, they must have stumbled on this particular screen. What can I help with you? And this is what can I help you with? And this is not coming from Maruf. This is coming from Siri. For those of us that are not using iOS, we equally have this on Android. Hi, how can I help you? It is called Google Assistant. And they do tasks that in robotics will have done for us. They perform tasks that without asking questions, without specifically stating what you want, by having a conversation with them, it helps you to identify what exactly it is that you are looking forward to. So moving on and on, we equally have autonomous driving, driverless cars. Tesla has invested so much in this, whereby we have cars that no one will be sitting in the steering wheel, and it will take you from your current location to your destination. This is happening already as we are talking. And we also have Sophia, which is an humanoid. It is more of a conversational artificial intelligence model depicted as a woman. Moving on, apart from these few ones that I have mentioned, we equally have application of AI touching all facets of human endeavor force. We have it in agriculture, translation, healthcare. Okay, we'll still be talking much about healthcare. We have it in manufacturing, traveling, finance. In fact, in finance, it has prominent application in stock prediction and equally in internet marketing, biopsy, biology, and so on. These are just some of the examples that we could be able to put together. In almost every aspect of human and therefore we have application. Even in reproduction, where we have to do some genetic phenotyping, artificial intelligence equally has application in them as well. And that beats the question, why artificial intelligence? The first thing that comes to mind is increased accuracy. It is able to bring a very big problem that ordinarily a human being might not be able to decompose by itself and solve it, and gives us the opportunity to make better decisions. So also, we must have heard about deep learning, artificial intelligence, and machine learning. How does it relate to each other? When we have a child, the mind, according to some philosophers, the mind of a child is a tabula rasa at birth, meaning that it is blank. A child is only as intelligent, as wise as the amount of information you feed into it. So artificial intelligence is equally a machine that we are hoping to train, just the way we train a child. And from there, we expect that such kind of machine will be able to make decisions, perform actions that are tantamount to what a child can perform. Moving on and on, machine learning itself, it is a subset of artificial intelligence. Artificial intelligence still has its own other categories like narrow AI, super AI, general AI, but machine learning is equally a subset of AI based on how we are learning it, how we are making it to understand this intelligence. It is giving the computer the ability to learn without being explicitly programmed. Explicitly programmed in the sense that we are not asking it to move 10 steps to the right, 10 steps forward, 10 steps backward. We are giving it data called labels and data called variables, and we are expecting it to make its own decision based on the data we are feeding it. What makes deep learning so different from machine learning is because of the fact that in deep learning, we are not specifying what our targets are, what our variables are. No, we are giving it those data and we are expecting it to make predictions based on this figure. We are just giving it data and asking it to figure it out by itself. So by and large, these features, they have their own applications based on the kind of data we have, based on the kind of problem we want to solve. It is a function of what kind of classifiers, what kind of algorithm we are going to be building. So deep learning is not superseding machine learning, and machine learning is not also less important than deep learning. They perform different tasks. It's just like an advanced, deep learning is just an advancement to machine learning. So coming to machine learning itself, it's a subfield of artificial intelligence. It expects human design and encode features that appear distinctly in the data. Algorithms are trained to perform tasks by learning patterns from data rather than explicit programming. Machine learning uses algorithms to learn from data and make informed decisions based on what it has learned. I've earlier explained this. Moving on, y equals mx plus c. We are all familiar with linear regression from plotting graph. This is part of the things we must have done in our elementary mathematics, whereby we are given coordinates of x and y, and we are asked to plot some values on the x-axis, plot some values on the y-axis, after which we plot our line of best fits to slicing the y-axis on our intercept, before we now finally arrive at this y equals to mx plus c, our m being the slope and our c being the intercept. Machine learning is typically like this, only that we are not having just one x. We might have just one y, but we can have as many as possible x. So when we have those kind of processes whereby we've earlier trained our data with a particular series of y and x to give us this our model, we come up with new values of x2. We plot it on this our line of best fit, and we have our corresponding values of y. But in all cases, we don't always have a line that best describes our values. We have some that will give us some sort of astronomical plots. We have logistic plots. We have polynomial plots. Not all of them are going to fall into a straight line graph. And y equals mx plus c only mimics values that falls into straight line. So this is part of what makes machine learning so diverse, because we have different classifiers that will be able to model a particular kind of, that will give us the particular kind of model based on the kind of data that we are having inside it. So by and large, different aspects, different components, but it still gives us the job. It gets the job done at the end of the day. Also, moving on to deep learning, it's a subfield of machine learning. I said earlier, we don't use feature engineering here. I'll still talk about radiomics, which is an integral part of feature learning itself. Instead, it allows the algorithm to learn on its own by classifying the best features from the data that we provide. It's also structured algorithm in layers to create an artificial neural network, which after it's finished learning, it can make decision on its own. It is mimicked after the way the brain operates based on the kind of neurons that we have in the brain, where it senses the data from the dendrite, and it passes this along the axion, and on the axion terminal we have our output, which is equal to what we have here. We're having our x input, there is a corresponding weight with it. We add our bias, we also have some sort of activation function that we add to it along the way before we now finally have our output. And equally, as we are having our output, there is also a feedback projection, that we equally have based on the loss that we must have computed, that how far is this output that we have from the real truth. We plot it back into the system and it continues retraining until we have an accurate, we also have metrics that we use in assessing our model to know that, okay, we now have them, that they can be able to adequately predict good results for us. And this is equal, on the right here is what is a mimic of how a typical deep neural network look like. While we have our input layer, we have our hidden layers, and we have our output layers. Moving on, convolutional neural network is only just one part of deep learning, but it's what we use most in artificial intelligence, in radiotherapy and radiology, as it applies to medical physics, which is why I'm trying to make some little explanation as it is concerned. It has a way of having different layers, have some sort of ReLU activation layer inside it, put some pool as well before you now finally have some sort of output. In this particular instance, we have a car that has been fed into our neural network. It is decomposed into various convolutions, and on the output, we're having different predictions with the percentage of certainty of each one of those predictions. Of course, anybody that knows this, a human, will identify this as a car, but a computer will not do that, which is why a computer is giving us this multiple option of car with almost like 99%, truck with like 44%, airplane with like 30%, ship, horse with various percentages. So, and how does it work? It decomposes each of these images into its own pixel. Anytime you take an image with your phone and you check on the details, you always have like two values with X at their middle. That's to tell you the resolution of that particular image. It is actually a box of color arranged together that is forming your picture. So convolutional neural network look at the analysis of these images, decompose it, and understand it based on its own capabilities, and gives us an output prediction of what it could likely be. And this is a further example of what we can use a convolutional neural network to do: semantic segmentation, classification plus localization, object detection, instance segmentation. Moving on as well, we also have feature engineering. Feature engineering gives us the ability to take an image and decompose it itself, but instead of making it to learn, like in the case of deep learning, extracting values from its pixels, and we are using machine learning models to understand those features. Earlier presenters have made mention of this. It is what we also refer to as radiomics, whereby we take a radiological image. Radiological image comes in forms of pixels, like how bright or how dark an image is. So instead of representing these spots in grayscale, we are taking a value of it. And those values, like the image we are having here, is just an ultrasound image, where we can take a particular section, convert it into arrays, into pixels, and take our values and use our machine learning algorithm to learn this particular model from which we can now make our predictions on. So by and large, this is a network map of all artificial machine learning algorithms that we have. It starts with regression to Bayesian to regularization, decision tree, reinforcement learning, ensemble. Deep learning is a fighter part, dimension reduction, neural network, instance-based, and clustering. You must have heard about random forest. You must have heard about k-nearest neighbors. For people who are involved in this, each one of these classifiers, they come under a particular section in this big map that we have in front of us. So for anybody to call himself an AI expert, he or she must have a broad knowledge of all items that is currently being displayed on the screen. Deep learning, convolutional neural network is just an item of what machine learning itself is all about. So it is broad, and the sky is the limit. You can there is no restriction to how big and how wide you can work on machine learning. And equally, the kind of data that we have is what determines what kind of model that we are going to do, what kind of model we are going to build, and what kind of algorithm we are going to use, and what kind of classifiers we are going to use. Earlier on, as part of the breakthrough of artificial intelligence, Go, the game Go, very popular in our Asian countries, a model was built to learn this particular game, and it beats the best human that can play this game in 24 hours after the model was created. So looking at this, there are a lot of limitless opportunities that AI can have when we apply it in instances whereby it is not even for entertainment, it is not gaming, but real life application that can make life easier for all of us. So by and large, AI has application in almost all facets of healthcare. Smart electronic record is the first item on the list, whereby it gives you the opportunity to look at patient records and make predictions based on the kind of information that is there: research, training, treatment, personalized medicine, decision-making, diagnosis, early detection, keeping well, radiology and radiotherapy. Radiology and radiotherapy is what I will be basing most of my conversations moving forward on, because it is what concerns us most as medical physicists. In applications, as part of its application in radiology, Nunit Insight developed an AI model that could be able to detect major lung diseases from ordinary chest X-ray. As it was able to successfully detect pneumothorax, it also detects tuberculosis, lung cancer itself. It was also able to detect some sort of nodules and calcifications in some other modules. But as far as what Lunit Insight did, they were able to actively get some sort of success, record some sort of success on this particular work that they did. So also, I remember Dr. Dada made mention of getting the age of a particular player by MR images. Yes, Vunomed bone age also did something similar as well, whereby they were able to only take an image of a particular person's hand, and they were able to put it into their model, and it was able to adequately and accurately predict the age of the patient. We also have application, Kang et al. They also develop a deep convolutional neural network that use directional wavelengths to perform active reconstruction on X-ray images that have earlier been taken with low doses. This perform two functions. It gives us the ability to have high resolution image, and it also gives us the opportunity to actively reduce the dose that patients will undergo when performing CT. As we all know, radiation, as Mr. Bayomi said, that as it can kill cancer, it can also cause some harmful effects as well. So we apply the principle of justification in all things that we do to make sure that the minimum amount of radiation dose possible is what we are able to use to get the maximum result obtainable. And this is their network architecture that they use. We are able to get the used four layer of architecture, and for different levels they have different convolution inside it, and we're able to use it to perform the noising to get their wavelength decomposition. Moving forward, we equally see their results here, whereby they are able to get the images where they will be able to, this is the image they get with the regular dose, this is the one they got with the low dose, and from the reconstruction that they did with their own algorithm, they were able to get high resolution images that are even sharper and brighter than what a regular dose will have given us. Moving on as well, auto-reporting is equally part of the things some scientists are working on currently as part of the application of AI in radiology, whereby they are able to feed in their DICOM images into their model and to prepare the reports for them. And on some aspect as well, it's also enabled radiologists to utilize AI as part of their normal PACS workflow. PACS is what radiologists use in making their reports, gives them the opportunity to look at their images and be able to adequately attend to them. Triaging studies also show that urgent reviews, they pop up easily. It enables radiologists to be able to attend to reports that are very important and they are time bound, more than the ones that can still take sometimes to attend to. Then intracranial hemorrhage are equally being worked on, characterizing pulmonary nodules on CT. Then it also helps to avoid unnecessary thyroid nodule biopsy. I saw of this research whereby it gives them the ability to detect calcifications, detect them to be able to make diagnoses that they could easily make without having to do further research, further investigation. So also as part of the application in radiotherapy, in fact, this is more or less like the winning light as far as AI in radiotherapy is concerned. It was done by Professor Lawrence Scott et al. And his team at the Cott Lab in MD Anderson Cancer Center in Texas. So they are able to develop a radiation planning assistant, particularly for LMICs, whereby they have shortage of professionals that could be able to handle this particular task. So all they need to do is just to make a plan order, whereby they select the dose, they give information about the patient, the diagnosis, the energy they intend to use, the kind of procedure they want to perform, the fractionation, and they equally give their CT images, undelineated CT images. It is this particular RPA that will do the segmentation itself and take the information from the plan order, do it, and in 30 minutes, it gives you a treatment plan with the documentation of the treatment plan itself. So this is a breakthrough achievement, and they've been making efforts to make sure that this particular model that they built was able to get implemented in all aspects of LMIs. I know it's already been it's been planned to be introduced in clinical practice in South Africa. I know there is an Electa site that they have there, and they are also planning to extend their coverage to other LMICs, not only Africa as well. Then also liver and liver tumor segmentation was also done by Lee et al., where Lee and his colleagues, whereby they make a particular unit, highly dense unit network, which gives them the opportunity to take CT images. They feed it with their data, whereby they were able to color this particular red spot with as the normal liver delineation, and these green spots as the one where we have the liver tumor, and they were able to extract a 3D model out of it. So they built their ArcNet, whereby they made they were able to concatenate a dense unit with an ArcNet, ResNet together, and they have a 3D dense unit to give them the opportunity of doing the liver segmentation and the tumor segmentation. So this is their results. When they feed it, this is the training data they use, whereby they fit in this particular image, and they were getting this. They fed this particular image as well. They got this and this. They fed this image too, and they fed this to the trained eye, especially somebody who has worked in radiotherapy for long. If you look at this particular CT slice, you are looking closely, you'll be able to see the dots, and those dots actually mimic where your AI model, the AI model is giving them the location of the liver tumor itself, and they were able to get an average score of 0.8602. It's an excellent research, and they perform fantastic well as well. So also, Samane and his team were able to work on prostate cancer, whereby they were able to carefully delineate prostate itself and then the organ matrix surrounding the prostate using this their network architecture, and they were able to get this. This is the CT image that they fed. This is the segmentation that their AI model gave them, and this is the grand truth that the radiologist earlier contoured, and overlaying both of them together, it is seen that for as far as the prostate tumor is concerned, the segmentation and the grand tool was able to match each other. And for the OARs as well, in the case of bladder, it's matched very well, and in the case of rectum, it's equally matched very well as well. Also, as part of application in radiotherapy, Elekta was able to give us MR-Linac, whereby they were able to do treatment planning on MR images. On a norm, what we do in clinical practice is to use CT images because of its electron density, which is a function of each tissue in a particular model. We do our dose calculation based on that electron density. So with what they did, they were able to convert MR model, the signals, they were able to convert it into pseudo CT images that gives them, that convert those signals into using GAN, generative adversarial network. They were able to get some sort of electron density for each pixels based on the signal intensity of each pixel on the MR image, and they were able to do their dose calculation based on that, and they were able to get a result between -3% to 3%. That's really fantastic, though it could get better, but this is a really great result. Then so also Kamunda and his team also were able to use an artificial intelligence model to do isotope destruction to detect an isotope in a particular X-ray based on the spectra. For this particular image that they have here, it was able to give the percentage contribution of each isotope and how they are composed, and they record a very substantial amount of success in this as well. So apart from this, tissue classification is equally part of the application, the way we've seen it in working in clinical practice as well. Cancer staging, it's apart from the TNM staging that we use, AI has proven very efficient to be able to tell us the stage of a cancer by feeding it its image as well. Apart from even feeding it its image, there are some instances whereby we did biopsy, and instead of a pathologist to report it itself, they were able to take the images of this slice of the biopsy, and they were as viewed under the microscope. They trained it, and it was able to give them the staging of the tumor itself. Then quality assurance is also being planned to be part of, some people are equally working on it to give us the opportunity to be able to detect faults before they happen, especially in machine. They were able to look at how often a particular item of Linac got damaged, how often it does, and they were able to build a model that will give a warning before it actually happened, and the engineer could actually fix it before the damage actually gets done. And outcome prediction is an item of application of artificial intelligence in radiotherapy as well, whereby we have the opportunity of looking at how long will a particular how much a particular patient is going to respond to treatment as well. By and large, I know we still have a lot of things to cover as far as AI is concerned, but it is hoped that one day physicians can be able to 100% say that with this, we'll be able to adequately treat a patient. Though we still believe that physicians treat, God heals, but AI is giving us that kind of opportunity to be able to look our patients in the eye and tell them that we've given them the best that we could. So by and large, I must have been mentioning modeling, and what exactly it's model. It is what we use to define after we've trained our data and we've put the appropriate classifier to do its work. It is what we refer to as our model. It becomes a model after it has been trained, after where the next step on the agenda for it is to bring our new test data to test it and report back. So how do we even get to build a model in the first place? The first thing you need to do is to define a problem. By defining a problem, you have to be able to adequately itemize what you hope to treat, what problem you hope to address, what things you hope to make easier. And after then, you set out to gather your data sets. Data sets are the most difficult parts of modeling, if I'm to say, but with various techniques, people have been able to still navigate those waters and get their data sets in order. Then we are also, after you gather your data sets, you clean it, because of course, from the sources that it is coming from, it might not be as, it might not be in its best for you to be able to train them very well. And where this is important is because if you don't clean your data set, it will give you a lot of errors in your prediction. You wouldn't even be able to treat it very well. You have to remove lot of data that are not particular to you. If you are having empty rows, empty columns, you delete them. After you have your clean data in order, you go ahead by building. And how do we build? We build by training the algorithm with our data. When we produce our model finish, we have an input data to test, we make a prediction, we compute our loss, our errors, then we feed it back into the system as well. Then after we are satisfied with what we have, we evaluate it. We have different metrics that we use. We have specificity, sensitivity, area under curve. We have quite an handful of them to determine how efficient and accurate our model is. And then we can deploy it. So far, so good. Most people have been deploying it as some sort of software. Some people are deploying it as an app or mobile. Some people are even deploying it as a standalone application on their own individual laptop, while some people are hosting it on a server on the net, where you can just type your address, your .com, particular thing.com, and you'll be able to feed in your data and get your prediction. So moving forward, getting started, how do we move from here? I must confess at this stage that everything I know about artificial intelligence are self-learned and things I learned on the internet. But these are like my arsenals, like what has been working for me so far. I've never sat down under anybody's tutelage to learn it. But when you are propelled by curiosity, you tend to go ahead and find things done irrespective of the means you have to get it. You make sure that you get it done as fast and as quick as you can. So the first item you need to learn is Python or R. I don't use R, I use Python, but either one you use, they are equally good. And then after you learn Python, there are a lot of courses on Coursera, on Udacity, on EDX that you can use that will give you the opportunity to learn Python very fast. When you are done with Python, you move to Jupyter Notebook. Jupyter, there are equally a lot of tutorials on how to install Jupyter. Jupyter is only like a notebook, but the fact that it is a notebook, it makes it more easier for us to work with machine learning projects faster compared to just writing a script in Python. It is very dynamic. If you make errors, you see it. You don't have to run the whole script before you find what your errors are. So after then, you can, if you run into any problem, Stack Overflow is good for you. You always, there is no problem you can run to that someone else has not run into that same kind of problem before. All you need to do is just to be able to adequately identify, like isolate the problem, so you know exactly what it is that you are asking. Then GitHub is equally there. Open an account with them. Then Kaggle is like the social media for data scientists. So sign up with it and just follow what is going on there. Then Twitter as well. Twitter is quite active. Of course, you can get distracted with Twitter easily, but there is a very strong machine learning, deep learning, artificial intelligence community on Twitter. Just try as much as possible to follow a few of them. From their tweets, you learn. Then equally, Colab is just another notebook hosted by Google. But Colab gives you the opportunity to be able to access some GPUs. Most laptops we have, they are CPUs. There are limitations with which you can do to the things you can do with your Jupyter. So, but when you have Colab, you can be able to host huge amounts of volumes of data, performs high computation on Colab, and it will still give you what you desired to achieve. Then also work very well with ResearchGate. There are a lot of articles, journals that people keep publishing on the daily. And when you see these articles, there is no way it's not going to stimulate you to be able to do more and more on this your journey to become a data scientist. You choose to accept this mission. Then also, Google is your best friend. It goes without saying. There is virtually nothing you type onto Google that you don't have. Moving on, there's nothing that doesn't have its pros, that doesn't have its issues as well. What are the issues that we face when coming into machine learning and deep learning and artificial intelligence? The first thing is high cost. These are fast. Thank God Google are giving us some sort of opportunity to work with their Colab. It is highly capital intensive. If you say you want to buy a laptop that has GPUs, in fact, it's very expensive. So, but there has been some ways with which we want around that. Unemployment, there is that scare that artificial intelligence can cause unemployment. At this juncture, I would like to borrow the word of Abayomi when he said that the artificial intelligence is not going to replace medical physicists, but medical physicists that uses AI will surely replace those that don't. It is true. It is true. When in a few years to come now, we'll see it happening. Then equally, your model is only as good as the data that you feed into it. It doesn't have its own original creativity. So some of these are limitations that we currently have, but the fact that there are limitations right now doesn't mean that they are not going to get solved in the nearest future. So all these things shouldn't mitigate you from embarking on your progress in trying to learn machine learning and be the best on it. So also, Stephen Hawking of blessed memory said that human efforts to create machines that can think are a huge threat to existence of human race, and the race to develop a complete human AI could mean that the human race would come to an end in the nearest future. Well, he's a theoretical physicist, of course, and most of the things that he's trying to say here are just trying to gesticulate into the future. Currently, we are doing narrow AI, and AI that is only as good as how much you train it. If I build a model that is applicable to tumor segmentation, if I don't train it to do treatment planning, it won't do it, and it can't learn on its own. And the fact that it's even doing treatment planning doesn't mean it does everything that AI can do in radiotherapy. Radiotherapy is only a subset of medicine, and medicine is only a subset of the larger general society that we have. So for us to get to that level of general AI, super AI, is still a long walk from what we currently have. And even if we achieve it, at that stage, we have something called Atomos Law, which is referred to as this law of robotics, whereby the first law, the second law has been put in place to make sure that there is no harm that can come from any artificial intelligence models to a particular human being. So there is nothing to be afraid of. AI is not going to take over the world, as people used to say. They are our tools. They are like armor, they are like chisels that we ought to use to make things easier for us. You can't have at home and be using your hand to be making hips. So these are just like a tool. We shouldn't be afraid of them, and we shouldn't think that it's going to take over our jobs. So by and large, as my conclusion, AI is doubtless the next big thing for medicine. Apart from radiotherapy, it has found application in surgery, it has found application in electromechanical recording, as I've said earlier. Companies that are more flexible, all of them, almost all through the globe, are adopting AI. Even people that are not primarily in medicine, like IBM, like Google. Google invested DeepMind to come into medicine. They are trying to see how much they can be able to put their heads together and make sure that AI works for medicine. And in fact, experts anticipate that implementing AI will soon be necessary for us to compete in all industries that we have. If there's any industry in the nearest future that doesn't have a particular solution running on AI, such kind of industry could be termed as archaic, just like all industries are required to have social media presence nowadays. So AI is becoming like the next big thing for us. So at this juncture, I would like to implore you, if you are scared of AI before, now is not the time to be scared of it any longer. So moving forward, I would like to thank the organizers for giving us this opportunity to at least present the little we've known to the general populace, and I would like to implore my brothers and sisters. Some of us don't have the opportunity of benefiting from a project like this when we are in our undergraduate, but we still thank God for where we find ourselves today. So for Dr. Eyobota to be putting heads together, like trying to make all these things happen, you really deserve a big kudos. Well done, ma. God is your strength. So it is at this juncture that I drop the curtain. If there is any questions, let me know. Thank you.